Chapter 5. In this video, we're going to look at one of the key factors that will determine what you grow, raise, and construct on your permaculture site. Climate. Fundamentally, the local climate conditions will decide which strategies you utilize in your design. So, understanding them is pretty important, and that's what we're going to explore today. Climatic factors are determined by many different things, from the shape of the land and altitude to the way global weather systems circulate around the planet. Indeed, it is at the planetary level that lots of things happen that can affect climate, such as the relative orbits of the Earth, Sun and Moon, astronomical phenomena such as solar flares and fluctuations in the Earth's magnetic field, and the changes to Earth's atmosphere caused by human activity. It is this last aspect that is likely to have the most consistently destabilizing effect on Earth and our actions at the local level, such as cutting down forests, polluting the seas, and burning fossil fuels, does have impacts on a global scale. It is very difficult to predict to a very precise degree what the effects will be. So it surely makes sense to always err on the side of caution and design local strategies for our sites that allow for variations in climate conditions. A simple method of doing this is to plant a wide variety of crop species so that if one is affected by adverse weather conditions, we have others that will survive. It's the don't put all your eggs in one basket approach. As permaculture designers, we want to have as much information as possible from which to make decisions. So we don't look at averages, we look at extremes. What are the limits of our local climate to which we can design? We need to use design techniques that are appropriate to our locations, so no forcing temperate species into a design for a tropical site, for example. And research our location before embarking on our permaculture plans. Local observation, local data sources, locally successful plant and animal species, and the experiences of local gardeners and farmers are extremely valuable inputs into your design process. And a good understanding of them will make a great platform from which to create a self-sustaining, reliable ecosystem. Climate zones. Now, despite the importance of looking at local factors, climate also works on a global scale, and understanding this larger canvas of weather events is essential background information for when we dig down onto the local level. We can broadly classify the globe into three types of climate zone, based on the interaction between radiation and precipitation. There are, of course, limitations to such broad classifications, such as the inability to gather precise data across large zones, the fact that averages in terms of things like rainfall and radiation don't reflect regional variations, and that climate factors continuously interact with conditions on the ground, such as coastlines, mountains, and local transfers of natural and man-made energy. But they do serve a useful purpose in understanding how temperature and precipitation affect plant growth and animal survival. Indeed, lots of information on growing plants comes with reference to zones of hardiness, which are typically based on these broad classifications. So, the three climate zones we use are tropical, temperate, and arid. The tropical classification refers to areas in which the mean temperature never falls below 18 degrees Celsius. We use the subcategory of subtropical for areas where the coolest months may fall below the 18-degree threshold, but never fall below 0 degrees. So, all the tropical areas are frost-free locations. The temperate areas consist of those where the coldest months see the mean temperature fall below freezing and the warmest months rise above 10 degrees Celsius. A subcategory is polar, which refers to those locations where even the warmest months are below 10 degrees. Arid zones are classified by their levels of precipitation and include anywhere where evaporation exceeds precipitation. It refers to areas where the mean rainfall is 50 centimeters or less annually. If rainfall is 25 centimeters or less, we call such areas deserts. We will explore design and planning strategies for each of these types of climatic zones in later videos. Global weather systems. Now let's take a look at how weather systems operate on a global scale, which affects where the tropical, temperate, and arid areas are. Differences in air pressure occur due to differences in the temperature of the atmosphere. And the differences in air pressure are what create wind. When air is heated, the air expands and is lower in pressure. This causes it to rise. Conversely, when air cools, it becomes denser, higher in pressure, and sinks. Because the surface of the Earth at the equator is closer to the Sun, it receives more heat, so has more high-pressure air. This warm air rises and produces clouds and storms as water vapor condenses, then moves towards the poles where it becomes cold and sinks before returning to the equator. If the Earth didn't rotate, that would be a simple circulation, but the spinning of the planet deflects these air circulations, creating spirals, more on which in a moment. so dense cold air flows off the polar ice caps in a spiral. Conversely, spirals off high-pressure airflow from the equator. At various latitudes, these systems interact with one another and the winds that they influence as well. In each of the hemispheres, there are three roughly delineated areas, or cells, where air circulations differ. The Hadley cell functions at low altitudes, roughly from the equator to 30 degrees north and south. Air is heated at the equator, rises in air columns, and then starts to move polewards. It is then cooled, sinks, and moves equatorward. This convection of air creates the tropical areas of the planet. The Ferrel cell is located between approximately 30 and 60 degrees latitude, both north and south. Here, air flows polewards near the surface and towards the equator higher in the air column. However, it is also a zone of mixing between the systems coming from the Hadley cell and those from the polar cells. Polar cells are, as the name suggests, those at the northern and southern extents of the planet. Here, air that arrives is cooled, sinks, and starts to move away from the poles. Within these cells are also the most persistent wind systems, which is another factor driving both the circulation of the weather systems around the globe and the circulation of the systems themselves in spirals. In the Hadley cells, we find the majority of strong trade winds, northeasterlies in the northern hemisphere, and southeasterlies in the southern, which can, in their interactions with the ocean and land, manifest themselves in storms, typhoons, and hurricanes. In the Ferrel cells, we find westerly winds. In both the north and south hemisphere, while at the polar caps, the winds are predominantly easterly. So, you can see that there are lots of air systems circulating in different directions, encountering winds from various directions and of various strengths. This makes for spiraling weather systems interacting with one another, and so fostering different climate conditions across different parts of the planet. But the effect is further complicated by the Coriolis effect. The Coriolis effect refers to the way that the spinning of the Earth deflects winds, causing them to spiral. The Coriolis effect is zero at the equator, half its maximum strength at 30 degrees latitudes, and at its maximum at the poles. Fast winds and winds covering the greatest distances are deflected the most. The effect causes winds to blow in circles, clockwise around high pressure and counterclockwise around lows in the northern hemisphere. While in the southern hemisphere, the effect is opposite, counterclockwise around highs and clockwise around lows. However, all this spiraling of weather systems is not just influenced by pressure differentials in the spinning of the globe. Other factors can play a part too. For instance, friction with land masses can slow weather systems down, while strong winds such as the jet stream can cut across the persistent winds and shift weather systems. Such impediments and disturbances can, for example, cause cold fronts to pile up against one another and cause cold front rains. At the southern pole, oceanic currents are central to the formation of between 12 and 18 cold fronts that spiral out of the ice cap, circling from east to west and reaching the southern coastal areas of South America, Africa, and the South Atlantic on a fairly regular 10-day cycle, with fingers of clouds circling out between them. Such regular cycles can also be seen in global weather patterns. Wind belts will move north and south over the course of a year as their position in relation to the sun changes, while it is also thought that the 18.6-year cycle of the moon's movement in relation to the Earth also has a significant impact. Such variations in air circulation influences the weather that different locations experience. And in the rest of this video, we're going to look at some of the climatic factors that play a part on a more local level. Precipitation. The first and arguably most important for permaculture design, given the essential nature of water to living things, is precipitation. There are two types of precipitation that can be inputs into our design: water falling from the clouds, in the form of rain, snow, and hail, and condensation. Both types are important to the design we use on our site, but rainfall is more than likely to be the predominant factor in our minds when providing moisture to our plot. One of the reasons we pay so much attention to it is that rainfall can vary significantly. While locations can have documented average rainfalls, they are also subject to wild swings in precipitation as rainfall is influenced by many local and larger factors. These include abnormal weather systems, pollution, and deforestation. Because we can't accurately rely on rainfall, and because it is arguably the key limiting factor in our ability to grow things, permaculture designers always seek to generate, conserve, or store water at every opportunity. We design so that our plot could, if necessary, withstand drier than normal conditions for a sustained period of time. Arguably, of most importance when planning for storage of water, it's data on rain distribution and intensity. Analyzing flood records, for instance, will give us guidance on the limits of placement of plant systems, fences, and buildings. Indeed, knowledge of potential flooding is essential to ensure no living elements on your plot are put at unnecessary risk. Another limiting factor associated with precipitation is available light. As precipitation rises, available light decreases. In some locations that are particularly clouded or humid, there's not enough available light for certain plant species to flower, while conversely, in drier areas, evaporation may exceed precipitation, drying out plants. Whatever the conditions on your plot, you can design to ameliorate precipitation shortfalls or excesses. So, it makes sense to try to understand the types of precipitation that you may be working with. Rainfall, for example, can be categorized into 3 types. They are orographic, which means the rain falls as a result of air rising over mountains and hills, cooling as it does so. Cyclonic, also known as frontal, which refers to rains coming from the interaction between cool air and warm air cells. And convectional, which stems from columns of hot air rising from deserts and oceans, then meeting cooler air higher up in the atmosphere. Precipitation also takes the form of dew. Dew occurs on clear nights and results from rapid radiation loss, meaning that moisture that is condensed from the atmosphere has not had sufficient radiation to evaporate. It is then deposited as drops on cold surfaces, such as the leaves on plants. Dew levels can vary due to a number of factors. For example, a slight wind, between 1 and 5 kilometers an hour, increases dew formation. Still, air or stronger winds reduce it, while if the ground is wet, this reduces the amount of dew that forms, as wet earth chills more slowly than dry ground. Dew has a counterpart that occurs on cloudy nights. The tips of leaves above warm ground can have a morning cover of moisture due to either guttation, which is water that has exuded from the leaves but not evaporated, or distillation, caused by water vapor rising from the ground and being trapped by the leaves where it condenses. In most places, dew is not a significant tool for the permaculture designer, as there will be sufficient rain across a year that, if harvested and stored, will provide for irrigation needs. But in desert areas, dew is often harnessed to aid cultivation. One traditional method is to assemble loose stacks of stones, the surfaces of which cool during the night, allowing dew to form, which accumulates to add moisture to the ground below in which plants can be located. A mound of stones can produce enough dew in this way to provide a tree with sufficient irrigation. A modern version is to use metal mesh fences as these cool rapidly at night. Even better for dew collection are shrubs of around 2 meters high. In natural deserts, you can often see shrubs fairly uniformly placed. Think about the matrices we talked about in the video about pattern, so that they are not competing for the same moisture. A designer could use a metal fence and plant shrubs along it to provide moisture for the plants as they grow from juvenile to adults. And once they are established, move the fence and begin again. Other techniques include planting trees in hollows, the sides of which are covered in volcanic cinders. The cinders provide a surface on which the dew condenses, and then it flows down to the base of the hollow to irrigate the tree. Differences in temperature also play a part in the formation of fog, which occurs when warm water evaporates into cold air. There are 3 types of fog, classified by the conditions under which they form. They are radiation fog, which refers to situations when the ground cools rapidly into clear skies, producing condensation. Advection fog refers to coastal and offshore fog that is caused by cold offshore currents condensing the moisture in warm oceanic air streams. And upslope fog, also known as orographic fog, which happens when humid air is carried to higher latitudes where the moisture in the air condenses as the air cools. While dew can typically only provide a very small quantity of moisture, fog can give significant quantities. In fact, some natural ecosystems function almost entirely because of the moisture provided by the fog. In New Zealand, for example, among mountainous areas that have a lot of upslope fog forests have developed because the canopies of trees are very effective at trapping the moisture and condensing it so it drips off the leaves and onto the soil where plants can access it. In areas where fog is persistent, some gardeners can even grow field crops without any other form of irrigation being necessary. Radiation. Solar radiation. There are 2 types of radiation from the sun that affect the planet: direct and diffuse. Direct solar radiation is sunlight that travels in a straight line from the sun to the surface of the earth. Diffuse radiation refers to sunlight that reaches the ground only after having been scattered by molecules and particles in the atmosphere. Diffuse radiation is more common at higher latitudes, with up to 30% of the total radiation reaching the Earth from latitudes 38 degrees or higher being this kind. At the poles, it can be close to 100%. While there is a small amount of energy that comes from heat radiating out from the Earth's core, the vast majority of radiation energy is from the sun. And it is this energy that, as designers, we tend to account for. Radiation is measured in wavelengths, with different lengths behaving differently. Short wavelengths are your ultraviolet rays, of which only a fraction gets through the ozone layer to reach the Earth. These are the waves that cause sunburn and, if you are excessively exposed, skin cancers. At the other end of the scale, the longer wavelengths are heat, radio, and infrared waves. These comprise about 50% of the radiation reaching the Earth and are also the wavelengths of heat emitted by objects that have been heated in combustion or that have absorbed shorter waves. Between these two extremes are the mid-range wavelengths. These are the various wavelengths that make up visible light. Usually this is simply seen as white light, but you can see all the different wavelengths that comprise white light in the colors of the rainbow. As each wavelength is differentiated by water in the atmosphere, these different wavelengths have different effects on plants as well, with the shorter wavelengths being harmful to growth, and very short ultraviolet waves even killing plants. Moving through good absorption for photosynthesis in the mid-range, while the long infrared waves do not influence growth, the plants just absorb them and transpire them as heat. This is not to say that all the radiation that leaves the sun and travels to Earth actually make it to our plots. If we assume that at the outer edge of the Earth's atmosphere, there's 100% of the radiation, about half of it is either scattered away from the planet by gases and dust in the upper atmosphere, or turned into long waves of heat and remains in the cloud of dust that encircles the Earth in the atmosphere, offering protection from the shortest wavelengths. The remaining 50% is what reaches the surface. The majority of it falls in the oceans and is either absorbed or reflected, but some, about 20%, falls on the land, and its energy is used to fuel the growth of plants and animals. The situation is made more complex by the effect that man-made population has. Not only does it influence the ability of atmosphere to protect us from harmful ultraviolet waves that are damaging to all life forms,